Everything you have been told about the universe might rely on a single, massive assumption that is actually wrong. We look up at the night sky and assume that what we see is a fair representation of the entire cosmos. We assume that space is pretty much the same everywhere, spreading out evenly in all directions. But a terrifying new theory suggests that our galaxy, the Milky Way, along with thousands of our neighbors, is trapped inside a colossal cosmic trap. We might be living inside a gigantic void. A bubble of emptiness so vast that it defies imagination. This structure is roughly 2 billion light-years across. If this theory is correct, we are living in the cosmic equivalent of a rural ghost town, far away from the dense, bustling cities of the universe where most of the matter actually resides. And the scariest part is not that we are isolated. The scariest part is that this void creates an optical illusion that has tricked our best scientists for decades. It makes it look like the universe is ripping itself apart faster than physics can explain. We think we are seeing the future of the cosmos, but we might just be looking at the walls of our own prison. This is not just a fringe idea anymore. It is becoming the only logical solution to a crisis that is currently tearing modern astronomy apart. We call it the Hubble Tension. It is a problem so severe that it suggests we either do not understand how the universe works, or we do not understand where we are in it. Today, we are going to explore the possibility that we are inside a cosmic hole, and how this realization changes everything we know about the Big Bang, dark energy, and the fate of reality itself. The story of this mystery is essentially a story about a map. Imagine you are trying to draw a map of the Earth, but you have never left your living room. You can look out the window, but you can only see your backyard. If you assume the whole world looks exactly like your backyard, your map of the Earth will be terribly wrong. For the last 100 years, astronomers have operated on a principle called the cosmological principle. It states that on a large scale, the universe is homogeneous and isotropic. That means it looks the same everywhere and in every direction. There are no special places. There are no privileged observers. But what if that rule is broken? Before we dive deeper into this mystery, I have a question for you. If it turned out that Earth was in a special, unique location in the universe that made our view of physics different from everyone else's, would you find that comforting or terrifying? Do you prefer to be average and safe, or unique and isolated? Drop your thoughts in the comments below. I read every single one, and the most interesting answers might get featured in the next video. And if you are the kind of person who loves cosmic mysteries like this, hit that red subscribe button. Because what I'm about to reveal next will change how you see the universe. Now, let's go back to the beginning. Our story begins in 1929 with a man named Edwin Hubble. Before Hubble, we thought the Milky Way was the entire universe. It was a static, eternal island of stars. But Hubble sat at the Mount Wilson Observatory in California, night after night, measuring the light from distant nebulae. He realized two things that shattered our reality. First, those nebulae were actually other galaxies, far outside our own. Second, and more importantly, they were moving away from us. The farther away a galaxy was, the faster it was retreating. This relationship is known as the Hubble constant. It is the speedometer of the universe. It tells us how fast space itself is stretching. If you run this film backward, you get a moment where everything was in the same place at the same time. The Big Bang. For nearly a century, the goal of cosmology has been simple. We just need to measure the Hubble constant precisely. If we know that number, we know the age of the universe, its size, and its ultimate fate. It sounds like a simple task. But it has turned into a nightmare. To understand why we might be in a hole, we first have to understand why our measurements are broken. Scientists have developed two main ways to measure this expansion rate, and this is where the trouble starts. The first method is like looking at a baby picture of the universe to predict how tall the adult will grow. We use satellites like the European Space Agency's Planck mission to look at the cosmic microwave background. This is the oldest light in the universe, emitted just 380,000 years after the Big Bang. By analyzing the patterns in this ancient light, we can calculate the ingredients of the early universe. We feed those ingredients into our best physics equations, the Standard Model of Cosmology, and we predict how fast the universe should be expanding today. The answer comes back very precise. The universe should be expanding at a rate of 67 kilometers per second per megaparsec. Keep that number in your mind. 67. The second method is completely different. Instead of predicting from the past, we measure the present. We look at the adult universe. Astronomers used the Hubble Space Telescope and the new James Webb Space Telescope to observe pulsating stars called Cepheids and exploding stars called Type 1a supernovae. These are what we call standard candles. We know exactly how bright they should be, so we can measure exactly how far away they are and how fast they are moving. When we measure the local universe using these stars, we get a different number. The answer is not 67. It is 73 or sometimes 74 kilometers per second per megaparsec. This might not sound like a big difference to you. 67 versus 73. Who cares? But in the world of precision physics, this is a catastrophe. It is a statistical impossibility. The error bars do not overlap. It is like measuring your height with a tape measure and getting 1 meter 80, and then going to the doctor and getting measured at 1 meter 95. One of you is wrong. Or maybe, the ruler itself is broken. By the way, something amazing is happening in the comments section. Last week, a user named Stellar Traveler asked an incredible question about whether the speed of light has changed over time. What do you think? Let me know below. The best comments get pinned, and I might even make a video answering your question. For years, scientists thought one of the measurements was simply wrong. Maybe the Planck satellite had a glitch. Maybe we were misunderstanding how Cepheid stars work. But as the data got better, the gap did not close. It got wider. The James Webb Space Telescope recently confirmed the measurements from the Hubble Space Telescope with insane accuracy. The tension is real. The early universe predicts one speed, but the local universe is moving much, much faster. This is where the panic sets in. If the measurements are correct, then our model of the universe is broken. We are missing something huge. Some unknown force or particle that is accelerating things in a way we did not predict. But there is another possibility. A possibility that is both elegant and disturbing. What if the problem isn't with the physics? What if the problem is with us? Imagine you are in a crowd of people. If the crowd is evenly spaced, and everyone takes a step away from you, the expansion looks uniform. But imagine you are standing in a clearing, an empty spot in the middle of the crowd. The people at the edge of the clearing are being pulled away from you by the density of the crowd further out. They would seem to be moving faster than they should be. This is the essence of the KBC Void theory. Proposed in 2013 by astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, this theory suggests that the Milky Way, Andromeda, and our local cluster are situated deep inside a relative void. We are not in a total vacuum, of course. There are galaxies here. But the density of matter in our region of space is significantly lower than the cosmic average. We are talking about a region that is perhaps 20 to 30% less dense than the rest of the universe. If this is true, it solves the Hubble tension instantly. Think about gravity. Gravity is an attractive force. Regions of space with lots of matter pull on everything around them. Regions with less matter have less pull. If we are inside a giant bubble of low density, and the outside of the bubble is a wall of high density, what happens? The galaxies around us are being pulled outward towards the high density walls. To us, looking from the inside, it looks like they are rushing away at incredible speeds. We interpret this as the universe expanding faster than it should. We measure 73 kilometers per second per megaparsec because we are seeing a local flow, a rush of galaxies exiting the void towards the dense regions. But the global expansion, the true rate of the universe, might actually be 67, just like the background radiation predicted. We are being fooled by our own address. This idea challenges the Copernican principle I mentioned earlier. It says we are in a special place. Not a magical place, but a statistical anomaly. A hole. And this hole is staggering in size. The KBC Void is estimated to be roughly 2 billion light-years in diameter. That is larger than the biggest superclusters we know of. It is so big that it is hard to even confirm its existence because we can barely see the edges of it. Now, here is where things get really strange. If we are in a void, it means our immediate surroundings are deceiving us. But to prove it, we have to count the galaxies. We have to map the density of the universe layer by layer, extending outward for billions of light-years. And when astronomers started doing exactly that, they began to notice a pattern. A pattern that should not exist if the standard model is correct. The number of galaxies seems to increase as we look further out. It is as if we are climbing out of a valley. This realization forces us to confront a dark possibility. If we have been misinterpreting the expansion of the universe because of this void, what else have we got wrong? For the last 25 years, we have believed that a mysterious force called dark energy is dominating the cosmos, pushing it apart. We invented dark energy to explain why the expansion is accelerating. But what if that acceleration is just a mirage caused by our position in the void? What if we invented a mysterious force that makes up 70% of the universe, just to explain an error in our perspective? What if we invented a mysterious force that makes up 70% of the universe, just to explain an error in our perspective? That is the question that keeps some astronomers awake at night. To understand the gravity of this situation, we have to talk about the elephant in the room. Dark energy. In the late 1990s, astronomers discovered something impossible. They expected the expansion of the universe to be slowing down because gravity should be pulling everything back together. But they found the opposite. The expansion is speeding up. To explain this, they postulated a new form of energy, dark energy, which acts as a sort of anti-gravity, pushing space apart. It is the foundation of our current standard model of cosmology, known as lambda CDM. But the KBC Void theory suggests that dark energy might be partially, or even entirely, a misunderstanding. Let's break down the physics of how a void mimics acceleration. Imagine you are standing in the exact center of a massive, spherical room. The walls are magnetic. You are holding a handful of metal ball bearings. If you throw them gently in all directions, they will travel away from you. But as they get closer to the magnetic walls, they will start to speed up. The magnets pull them faster and faster the further out they get. Now, replace the room with the universe. The magnetic walls are the regions of high density, the superclusters of galaxies that surround our void. The ball bearings are the galaxies we observe. As they drift from the empty center where we are, towards the dense edges, gravity from those massive outer walls grabs them and pulls them faster. To an observer sitting in the center, us, it looks like the galaxies are accelerating away from us on their own. We see them speeding up and we think, some mysterious energy must be pushing them. But in reality, nothing is pushing them. The dense matter far away is simply pulling them. We mistake the pull of gravity for the push of dark energy. This is a game changer. If we are inside a deep enough void, we might not need dark energy to explain the local universe observations. We just need good old-fashioned gravity and a very specific map of our neighborhood. But this brings us to the evidence. Is there actually a void here? In 2013, Keenan, Barger, and Cowie decided to count galaxies. But counting galaxies is tricky because space is filled with dust that blocks visible light. It is like trying to count houses in a thick fog. So, they used observations in the near-infrared spectrum, specifically the K-band. Infrared light cuts through cosmic dust like a knife. It allows us to see the old, massive stars that make up the bulk of a galaxy's mass. When they mapped the galaxy density relative to our distance, they found a clear trend. The density of luminous matter was low nearby and rose significantly as they looked further out to about 1 billion light-years or more. They concluded that the density inside this bubble is about half of what it is outside. That is a massive difference. In the delicate equations of cosmology, a 50% difference in density is enormous. It creates a significant gravitational outflow. This outflow adds on to the natural expansion of the universe. When we measure the Hubble constant locally, we are measuring the natural expansion plus this void-induced outflow. That is why we get the number 73. But the Planck satellite, looking at the early universe before voids formed, only sees the natural expansion. That is why it gets 67. Suddenly, the tension vanishes. Both numbers are correct. They are just measuring different things. If this theory is so perfect, why isn't every scientist shouting it from the rooftops? Why is it still controversial? The answer lies in the philosophy of science. Accepting the KBC void means violating the Copernican principle. For centuries, science has progressed by assuming we are not special. Earth is not the center of the solar system. The Sun is not the center of the galaxy. The Milky Way is not the center of the universe. Assuming we are average allows us to take a sample from our backyard and apply it to the whole cosmos. The KBC void theory demands that we accept we are special. It requires us to be living within a structure that is exceptionally rare. Standard cosmological simulations show that voids do exist, but a void this large and this deep is incredibly unlikely. It is a statistical outlier. Critics argue that the odds of us landing in the exact center of such a rare beast are 1 in a million. If this information blew your mind, hit that like button. It tells YouTube's algorithm to show this video to more curious minds like yours. Together, we are building a community of people who aren't afraid to ask the big questions. And trust me, what I'm about to tell you next is even more mind-blowing. There is a counter-argument to the critics. They say it is unlikely we are in a void. But we exist. We are observers. Life requires specific conditions. Perhaps life is more likely to evolve inside a void. Think about it. High-density regions of the universe are chaotic. They are packed with galaxies colliding, supermassive black holes feasting, and intense radiation. A quiet, low-density void might be the safest place for a solar system to stabilize and for life to emerge. This is called the anthropic principle. We observe the universe from a void because a void is one of the few places calm enough for observers to exist. If we were in the dense wall, we might not be here to ask the question. However, the debate is heating up. Recent studies have tried to disprove the KBC void. Some surveys, using different types of standard candles like supernovae, claim the void isn't deep enough to explain the full Hubble tension. They argue that even with the void, there is still a gap in the numbers. Yet, other anomalies support the idea that our local patch of space is weird. Have you ever heard of the CMB cold spot? When we look at the cosmic microwave background, the heat map of the early universe, we see a massive region that is unusually cold. It is much colder than statistical models predict. For years, this has been a mystery. But if there is a supervoid in that direction, or if we are connected to a complex network of voids, the light passing through these empty regions would lose energy, creating a cold spot. And then there is the dipole repeller. Astronomers have mapped the flow of galaxies in our local universe and found that we are moving. We are hurtling towards a dense region called the Shapley attractor. But we are also being pushed away from a region in the opposite direction. A region that seems to be totally empty. It acts as a repeller. This confirms that density differences drive the motion of galaxies on massive scales. We are caught in cosmic currents that we are only just beginning to map. So we have a standoff. On one side, we have the standard model with dark energy. It works very well for the large-scale universe but fails to explain the local tension. It assumes we are average observers in a uniform cosmos. On the other side, we have the void theory. It explains the local tension perfectly and challenges dark energy, but it requires us to live in a 1 in a million location. It is a choice between bad physics or bad luck. But there is a third option. An option that is even more radical. What if both are wrong? What if our understanding of gravity itself is flawed? Some physicists are looking at modified Newtonian dynamics, or MOND. They suggest that at low accelerations, like those at the edges of galaxies or in the vast emptiness of voids, gravity behaves differently than Einstein predicted. If gravity changes its behavior on these massive scales, then the voids would expand differently, and the way we measure distance would be completely off. We are standing at a crossroads in human history. For the first time, our instruments are sensitive enough to detect the cracks in our understanding. The James Webb Space Telescope is pouring gasoline on the fire. Every month, it sends back data that challenges the standard model. It finds galaxies that are too big and too old to exist in the early universe. It finds expansion rates that simply do not fit. We are building a house of cards, and the wind is picking up. If the KBC Void is real, it means the universe is far more complex and clumpy than we assumed. It means our maps are distorted. It means we are like sailors in the middle of the ocean, thinking the waves around us represent the whole world, unaware of the continents and currents just beyond the horizon. But what if this void is not just a random structure? What if it is a hint about the true shape of the universe? Some theorists have proposed that our universe might be a bubble among many bubbles. A foam of realities. If we are in a void, could it be that our void is actually the collision point between our bubble and another? As we prepare to look at the big picture, ask yourself this. If we really are in a cosmic cage, a bubble of emptiness billions of light years wide, how do we get out? Can we ever see what lies beyond the walls? Or are we forever trapped in this local illusion, destined to misinterpret the cosmos because of our isolation? The implications of this go beyond just numbers and graphs. It touches on the very nature of truth. If our perspective is flawed, is objective truth even possible? If our perspective is flawed, is objective truth even possible? That is the terrifying philosophical precipice we are standing on. If the KBC Void theory is proven correct, it means that for the last century, we have been trying to measure the infinite cosmos with a ruler that is bent. We have been building models of the universe based on a local hallucination. This brings us to the most profound consequence of living in a cosmic hole. The potential death of dark energy. For the last 2 decades, dark energy has been the dominant force in our understanding of reality. We believe it makes up 68% of the total energy in the universe. We believe it is tearing space apart. We believe it will eventually lead to the Big Rip, a terrifying end scenario where galaxies, stars, and eventually atoms themselves are torn asunder by expanding space. But if the apparent acceleration of the universe is just a side effect of matter flowing out of our void, then dark energy might not exist at all. It might be a mathematical ghost. A phantom variable we added to our equations to make them balance, simply because we did not realize we were standing on a tilted floor. Think about what that means. If dark energy vanishes from our theories, the fate of the universe changes instantly. We go from a universe destined for a cold, lonely, ripped-apart death, to a universe that makes sense again. A universe dominated by gravity and matter. It might mean the cosmos is more stable than we thought. It might even mean that the expansion could one day slow down, stop, and reverse, leading to a big crunch and a new Big Bang. Our location in the void might be the only thing hiding this cyclical destiny from us. However, this solution comes at a steep price. To get rid of dark energy, we have to abandon the idea that the universe is simple. We have to accept the inhomogeneous universe model. Currently, our math assumes the universe is like a smooth soup. Mix it up, and every spoonful is the same. But the void theory suggests the universe is more like a block of Swiss cheese, or a giant cosmic sponge. It is full of knots, filaments, walls, and massive, gaping holes. Doing physics in a Swiss cheese universe is incredibly difficult. The equations of general relativity become nightmares to solve when density changes drastically from one light year to the next. Perhaps we have clung to dark energy not because it is true, but because it is easier. It allows us to keep our simple, smooth equations. Accepting the void forces us to do the hard work of mapping every bump and dip in the fabric of reality. What we have covered today is just the beginning of a much bigger story. Next week, I am releasing a video about that axis of evil, a strange line in the cosmic microwave background that seems to align perfectly with Earth's orbit, defying all laws of probability. Is it another glitch, or are we in a simulation? The findings are absolutely shocking. Make sure you turn on notifications so you don't miss it. Click that bell icon right now. Because the universe still has so many secrets to reveal. So, how do we solve this mystery once and for all? How do we prove if we are in a hole or if physics is broken? We are currently entering the golden age of cosmic cartography. Right now, humanity is launching a fleet of new eyes into the dark. The European Space Agency has launched the Euclid mission. NASA is preparing the Nancy Grace Roman Space Telescope. These are not just telescopes. They are survey machines. They are designed to do one thing: map the darkness. Euclid is scanning billions of galaxies across more than a third of the sky. It is creating a three-dimensional map of the universe that extends 10 billion light-years deep. If there is a density wall at the edge of our KBC Void, Euclid will see it. It will see the galaxies piling up at the boundary like cars at a toll booth. It will measure the speed of galaxies at different distances with unprecedented precision. If Euclid finds that the galaxy density evens out and becomes smooth just past the 2 billion light-year mark, then the void theory might die. We will be forced back to the drawing board to explain the Hubble tension. But if Euclid sees that the density continues to fluctuate, that we are just one bubble in a frothy, chaotic ocean of bubbles, then the standard model of cosmology will collapse. We will have to rewrite every textbook written since 1998. This brings us to a humbling realization about our place in the cosmos. We used to think the Earth was the center of everything. Then we moved to the Sun. Then we realized we were just one star in a galaxy of billions. We learned humility. But now, the universe is teaching us a new kind of humility. It is telling us that average does not exist. If the universe is a complex web of voids and filaments, then every location is unique. Every observer sees a slightly different version of the truth. An alien civilization living in the dense coma cluster would see a universe dominated by gravity and collisions. They might never discover the expansion of the universe because everything around them is crashing together. We, living in the lonely quiet of the KBC Void, see a universe flying apart. Who is right? Both of us. And neither of us. We are like two people arguing about the weather, but one is standing in the Sahara Desert and the other is in the Amazon rainforest. The local conditions define our global philosophy. This suggests that there is no God's eye view of the universe. There is only the view from where you are standing. And where we are standing seems to be a very lonely, very empty place. But there is a silver lining to this isolation. If we are indeed in a massive void, it might be the reason we are here at all. As I mentioned briefly in part 2, dense regions of the universe are dangerous. High radiation, frequent supernovae, gravitational disruptions. It is hard for a solar system to remain stable for 4.5 billion years in a cosmic construction zone. Maybe life requires emptiness. Maybe intelligence can only emerge in the quiet backwaters of the universe, shielded by billions of light-years of nothingness. In that sense, the KBC Void is not a prison. It is a sanctuary. It is a cradle. We are alone because we need to be alone to survive. This leads us to speculate about the future of humanity. If we are in a void, and the galaxies around us are rushing away toward the dense walls, our view of the universe will eventually go dark. Billions of years from now, the expansion or the flow toward the walls will carry the other galaxies beyond our horizon. Future astronomers born on Earth will look up and see only the stars of the Milky Way. They will think our galaxy is the entire universe. They will have no way of knowing about the Big Bang, the void, or the other clusters. We are living in a privileged moment in history. We are living at a time when we can still see the walls of our prison. We can still see the light from the distant clusters before they fade away forever. We have the unique opportunity to decipher the code of the cosmos before the evidence is erased by time and distance. So, let's summarize the staggering journey we have taken. We started with a crisis. The Hubble tension. The fact that our two best methods for measuring the universe give two different answers. We looked at the proposed solution. The KBC Void. The idea that we live in a bubble of emptiness 2 billion light-years wide. We saw how this void mimics dark energy, creating an illusion of acceleration that has fooled the world's greatest minds. We realized that if this is true, dark energy might be a myth, and the universe is far more complex and structured than we ever dared to imagine. And finally, we are left with the philosophical fallout. That our location dictates our reality. That we are trapped in a perspective that we are frantically trying to correct before the lights go out. This theory, whether right or wrong, teaches us the most important lesson in science. Never assume you have the full picture. Just when we think we have the universe figured out, it throws a curveball. It reminds us that we are small, that our time is short, and that the darkness is full of surprises. We are inside a cosmic hole. And for the first time in human history, we are realizing that the hole might be the only reason we can see the light. I want to leave you with one final, deep question to ponder tonight. If we prove that our location distorts our understanding of physics, and that aliens in other parts of the universe would discover different laws of nature, does that mean that physics is not universal? Is it possible that there is no single theory of everything, but rather a million different local theories, each true only for its own bubble? So, what is your answer to that question? Is math universal, or is it local? Drop your thoughts in the comments. I can't wait to read them. And if you enjoyed this deep dive into the KBC Void, you will love my video about the Great Attractor. It explores the terrifying force that is pulling our entire galaxy across the universe at millions of kilometers per hour. The link is in the description, or you can click the card appearing right now. Until next time, keep looking up.